In the gold rush of 1849, prospectors found a yellow mineral that appeared to be gold, but was harder and more brittle than gold. What is this mineral that became known as fool's gold? Well, this mineral you see right here in the picture did look a lot like gold, but it had a couple major differences. It was harder and more brittle, but it was also had quite a difference in density. This mineral is not sulfur. Remember, that's the yellow one that kind of has a funny smell to it. It's not copper. It's definitely not calcite. Remember, that was the mineral that reacted strongly with the acid. That was, was more square, had three-dimensional cleavage. This mineral is called D-pyrite. The breakdown of rocks and minerals into small particles. Remember what that is. That's weathering. And remember a difference between weathering and erosion. Erosion is carrying away the broken sediments to a new location, and weathering is the actual process of breaking it down. So now you have to think between two options. There's two types of weathering. There's mechanical weathering and chemical weathering. So this question is asking you to decide which one is breaking a rock down into smaller particles without actually changing the chemical composition of the rock. So our answer here is mechanical weathering. And these pictures show you a few examples. This right here is called frost wedging. What happened here, you had some water seeped into a crack, and when the water got really cold at night, it froze and it expanded and it further broke this crack open. This process happens over and over and over again and eventually splits a rock in half. Down here in the bottom left, we have a very, very odd shaped rock that you'll find in the desert. All of the sand has been picked up by the wind and it's been blown against the rock down at the bottom, and it wears away the bottom. That was called abrasion. Then you just have a river here where we got fast moving water that has rocks banging into each other and tumbling and being broken down. So our answer is H, mechanical weathering. The streak test that is used to identify minerals involves studying we just got to know what the streak test is. If you remember in class, what we did is we took minerals and we rubbed them on this white ceramic plate and we checked to see the streak that was left. Intuitively, you may think that it would always be the same color, but sometimes minerals have a false exterior that you're not sure what the true color of the mineral is. This is a way to tell. And a great example of this is gold and pyrite. So actual gold will leave a gold streak, and pyrite, which was fool's gold, which is just sulfur and iron, will leave kind of a blackish streak. So the streak test that's used to identify the mineral involves minerals crystals with a microscope? No. Heated minerals color as it cools? No. Appearance of the mineral under a fluorescent light? No. Or the color of the powder form of the mineral? And the answer is J. This is a good question. It'll really test if you really understand the different types of rocks. So which of the following may preserve ancient remains of plants and animals? So what we're talking about here are fossils. So which type of rock may you find a fossil in? A granitic intrusion. Remember, granite is an igneous rock formed under the ground by hot magma cooling. You're not going to find any plants or animal remains in that. Volcanic ash. Volcanic ash. Let's think about that one for a second. And let's go to C, foliated schist. Remember, that's a metamorphic rock that has been bent and warped and changed by heat and pressure. Not going to find any fossil remains in that. Folded gneiss. That's also a very high-grade metamorphic rock, often found where mountains are colliding. So, if volcanic ash falls over the animals and buries the animals in it, you're going to find a fossil there. So, the answer is B, volcanic ash. Metamorphic rocks with a layered or banded look are called, and remember, metamorphic rocks come in two major categories, foliated and unfoliated. If you look at this picture over here, you see these very distinct light and then dark bands, the alternating layers. When you have distinct layering, folding, or bands, we're talking about a foliated rock. An unfoliated metamorphic rock does not have any of these distinct, obvious layers. So the answer here is A, foliated metamorphic rock. Okay, the rock cycle. The rock cycle is the process of changing one type of rock into another type of rock into another type of rock, and eventually it melts back into magma, and the whole cycle goes again and again. So this question is, which of the following processes will change a sedimentary rock into an igneous rock? Well, it honestly doesn't matter which type of rock we're talking about here, sedimentary or metamorphic rock. The only way we can get an igneous rock is the cooling of lava or magma. So, our possibilities here: melting and crystallization, sounds alright. Erosion and deposition, no, that's how you get sedimentary rocks. Deformation and deposition, very likely another way you would be getting some sedimentary rocks. Faulting and fracturing, no. The only way that we can turn a sedimentary rock back to an igneous rock is to melt it back to lava and magma. And our answer would be A, melting and crystallization. Obsidian, pumice, and scoria are all extrusive igneous rocks. If you remember these a little bit, this is pumice right here. This was that very, very lightweight rock that was full of air holes. It was so light, in fact, that its density is less than water and it actually will float. Scoria is very similar to pumice, but remember, scoria was a little bit heavier, higher in iron content, darker version of pumice. Obsidian, you might remember, was the very, very shiny, glass-like black igneous rock. What these three all have in common is they're extrusive, outside the earth, igneous rocks, which means they cool very, very quickly. And because they cool very, very quickly, they did not develop crystals, so they are aphanitic. And the answer here is G. They cooled too quickly to form crystals. So the picture above is labeled an igneous rock. The rock shown is composed primarily of large crystals that were formed by, there's lots and lots of ways you can get this question right. The first way is just to know an igneous rock comes from the cooling of lava or magma. Magma if it's an intrusive igneous rock, and lava if it's an extrusive igneous rock. Since our only choice is magma, compacting shells, and that's sedimentary rock, no crystals there. Weathering, faulting, the only possibility here is A, the cooling of magma. And just remember, the cooling of magma is very, very slow, and that gives a rock time to form these crystals like granite that makes like such lovely countertops. Which mineral is easily identified by smell? Well, most people feel that this yellow mineral right here smells a lot like rotten eggs. And this yellow mineral, if you remember from class, is J, sulfur. It's used very commonly in fireworks, so if you notice the smell of fireworks, it's kind of the smell of burning sulfur. It does have a very distinct odor to it. Hopefully you remember that. When granite is subjected to high enough amounts of heat and pressure to change it but not melt it, granite changes into heat and pressure. You just need to remember, when you see those key words, heat and pressure, we're usually talking about the formation of a metamorphic rock. And if you look at your more complicated version of the rock cycle here, we have melting, which turns into magma, which the cooling of magma makes an igneous rock. And then an igneous rock can get weathered and eroded away and turn into sediments and eventually made into a sedimentary rock. Or an igneous rock can get squeezed as two mountains collide. Or it can find an underground like plume in the mantle, like an underground chamber of magma, and it can get really hot and it can get baked. And it can directly take some heat and pressure, and that would turn it into a metamorphic rock. So our answer here is when any rock is subjected to high amounts of heat and pressure, it's usually changed into a metamorphic rock. Which of the following rocks represents an igneous intrusion? Now, an intrusion is when, think of the word intruder, so a rock that's breaking through the other layers of rock. It's intruding into the other layers. So there's two ways you can figure out the answer to this. One, which rock is intruding through the other ones? And the answer is granite. The other way you can know the answer is it gives you a hint. It tells you it's the word igneous, an igneous intrusion. Marble, shale, and limestone are not igneous rock. Marble's a metamorphic rock. We have shale and limestone, two sedimentary rocks, and granite's the only igneous one. But just remember what an igneous intrusion is, and that's really when we have magma underground that starts to seep or find its way through other layers. So if you look right here, we have an example in this picture, and you can kind of also see an example of it right here in this animation. So our answer is A, granite. The diagram shows a test for which mineral property? So if you look at the picture, what he's trying to do, he's trying to scratch this mineral right here with his fingernail. Then he tries to scratch it with a penny. Then he tries to scratch it with a steel knife. Basically what he's trying to do here is see how hard the mineral is. If his fingernails scratch it, then the mineral is probably a very soft mineral like talc. If a penny can scratch it, well then you know it's probably one of the softer minerals, but maybe at least one of the top 4 or 5 here. If a steel knife can scratch it, but a penny can't, then we're looking at one of the significantly harder minerals down in this area. So the diagram shows a test for which mineral property? The answer is A, hardness. Scientists use the rock cycle to describe the processes by which, well, what's the rock cycle? The rock cycle is transforming a rock from an igneous rock to a sedimentary rock through processes such as weathering and erosion, sedimentation, compaction, cementation. It's taking a sedimentary rock and heat and pressurizing it and turning it into a metamorphic rock. Taking a metamorphic rock and subducting it into the Earth's crust and having it melt into magma, and then that can cool and turn back into an igneous rock, and then this goes around and around and around. So just look at the best choices we have to offer. All different types of fossils were transformed into rock? No. One type of rock can be changed into another type of rock? B. That's definitely the answer. That is absolutely our best choice here. The answer is B. One type of rock can be changed into another type of rock. Okay, we got the Mohs hardness scale. Talc, which is a mineral, has a hardness of 1. That's the softest mineral we have. If you remember talc, and you just take talc and you just rub it together, it'll break apart into a powdery substance, almost like a baby powder, talcum powder. And then on the other end of the scale, we got a diamond. A diamond has a hardness of 10. A diamond is so hard that it will scratch all of these other minerals, and none of these minerals could put a scratch on a diamond. So according to Mohs hardness scale, which of these groups of minerals can scratch fluorite? Well, remember fluorite is a 4. So fluorite would be able to scratch talc, gypsum, and calcite because they are a 1, 2, and a 3. But fluorite would not be able to scratch any of the other minerals: apatite, orthoclase, quartz, topaz, corundum, and diamonds. But all of these minerals I just mentioned, the 5 through 10 minerals, they would all be able to scratch fluorite because it's got a less on the hardness scale. Alright, so let's look at our choices. Remember what we're asking here. Which of these groups of minerals can scratch fluorite? Talc, gypsum, and calcite? No, none of those 3, 1, 2, and 3 are able to scratch fluorite. Calcite, quartz, and topaz? 2 of them could scratch fluorite. Quartz, which is a 7, and topaz, which is an 8. Apatite, orthoclase, and corundum? Absolutely. All three of them are higher in the Mohs scale of hardness than fluorite. So the answer here is H. The density of a mineral is determined by its mass and, this is an easy question, hopefully you remember from the very beginning of the year, the density of an object, which is how heavy it is compared to how big it is its mass divided by the space it takes up, or its volume. So its weight divided by its volume. So the density of a mineral is determined by its mass and volume. In which type of rock are fossils most likely to be found? This is an easy one. You will only find fossils in one of the major types of rocks. An igneous intrusive rock, that's magma cooling under the ground very slowly. You're not going to find fossils in underground magma chambers. An igneous extrusive rock, that's lava. You're also very unlikely to find fossils in lava. The temperatures are just too high. So when lava cools, it's just going to be a rock. Sedimentary rocks? Absolutely. This is your answer. Sedimentary rocks are loose sediments that animals and plants' remains can become lodged in and turn to rock. Metamorphic rocks? Too much heat and pressure for there to really be a good fossil display. The picture here shows a sedimentary rock known as limestone. Which observation best shows that the limestone was formed from ocean sediments? So when you look at this rock, what observations can you make that would suggest to you that this rock or this rock on this picture came from the ocean? And the answer is obvious. It's not the thickness of the rock layers. It's not how many fossils there are, 1, 2, 3, 4, but it's the type of fossils that are in this. So our answer is H, the type of fossils. When you see marine fossils, such as all these shells, it strongly suggests that this rock was formed in the ocean. So which kind of rock is formed by the processes shown here? So we have a mountain range, and we see that rocks are being broken down by weathering. They're being carried away through erosion, and they're being deposited or dropped off along the coast. So what type of rocks do we have that are made through weathering and erosion, transport, deposition, burial, compaction, and lithification, meaning turned to stone? And that's a real easy one if you know your three basic rocks. And the answer here is G, a sedimentary rock. Because remember, igneous rocks are from lava and magma, and metamorphic rocks are from heat and pressure. G, sedimentary rock. The chart shows the Mohs scale for measuring the hardness of a mineral. So a mineral that can scratch fluorite, find fluorite, so all the minerals that can scratch fluorite, which is a hardness of 4, would be the minerals below it. 5, 6, 7, 8, 9, and 10. So a mineral that can scratch fluorite, which we know is minerals 5 through 10, and be scratched by orthoclase. So what can be scratched by orthoclase? Alright, so orthoclase is a 6. Right here, there's orthoclase. What can be scratched by orthoclase? Well, all the ones above it. 1, 2, 3, 4, and 5. So, if you look at this one more time, a mineral that can scratch fluorite, it's got to be one of these down here, but be scratched by orthoclase, which has got to be one of the ones up here. There's only one that's a possibility. 5, apatite. Once you know the mineral they're talking about in this question is 5, apatite, you'll be able to answer the question. So, a mineral that can scratch fluorite and be scratched by orthoclase, apatite, is able to A, scratch both calcite and quartz, Can apatite scratch calcite? Yes, because apatite has a hardness of 5, calcite has a hardness of 3. Can apatite scratch quartz? No, because quartz is a harder mineral. Alright, so can apatite be scratched by both calcite and quartz? No, for the exact opposite reasons. Apatite could not be scratched by calcite because calcite's a softer mineral. Alright, so can apatite scratch calcite? Yes. Can it be scratched by quartz? Yes. Because apatite has a hardness of 5, it can scratch a number 3 calcite, but it would be scratched by a number 7 quartz. So our answer here is C. It's a very complicated question. Which of these mineral properties cannot be used to identify a mineral? So let's look at all these properties of a mineral real fast. We have the hardness, remember the Mohs scale of hardness of 1 to 10, like talc to a diamond. That can help you. Cleavage, how a mineral breaks. Does it break into flat sheets? Does it break into three-dimensional squares? Or does it break into like irregular chunks? Its luster, kind of how shiny it is. Its color can be helpful. The streak that's left on the streak plate can be helpful. There's lots of things. Its density, its specific gravity, that can be helpful. What cannot be helpful? Luster, we said yes. Hardness, we said yes. Streak, we said yes. But its mass, its mass cannot be helpful because it doesn't matter how big the mineral it is. That won't tell you how much it weighs or how big it is. That's not going to tell you what mineral you have. So the answer is H, mass. Rocks formed by the cementing of weathered materials are called. Just got to remember your rock cycle a little bit. Which rocks are formed from eroded sediments, eventually compacting in the bottom of the ocean and getting glued together by minerals, cementation. This whole process of weathering and erosion and compaction and recrystallization, cementation, this is all the processes involving A, sedimentary rocks. Just remember, igneous rocks are a result of the cooling of lava and magma. Students on a geology field trip will identify minerals by their streak. Which of these should the students bring on a field trip? Remember, if you're going to do the streak test, it's very simple, not a lot of equipment needed. You need a white ceramic plate to rub the mineral on and see the true color of the mineral. So do you need a long pointed iron rod? No. A rough white ceramic tile? Looks good. A disposable sample of talc? No. A low-powered telescope? No. You need B, a rough white ceramic tile. Of these igneous rocks, which would contain the largest crystals? So we gotta look at our chart here, and we see our type of lava and magma, basaltic, andesitic, and granitic. And then we see intrusive and extrusive. You have to know which rock forms crystals. And the answer is it's intrusive rocks. Intrusive igneous rocks are formed from the cooling of magma underground. That magma under the ground cools very, very slowly over millions of years, and as it cools so slowly, crystals develop. Extrusive igneous rocks over here form from lava that's on the exterior surface of the earth, and it cools very quickly and does not have time for the formation of crystals. So of these igneous rocks, which would contain the largest crystals? So what we got to do is we got to choose from the intrusive group. And luckily, our choice is simple. A, granite. The other three are all extrusive igneous rocks. So igneous is the only intrusive phaneritic igneous rocks that has crystal development. So our answer is A. Slate is a fairly common rock that can be used for roofing shingles. What property makes it most suitable for this use? Well, if you look over here at the picture, this is a man that works with slate to make for roofs, And what he's doing is he's taking this foliated or layered metamorphic rock and he's splitting it along its cleavage plane. And slate splits very, very easily in very flat sheets. And remember, for a roofing shingle, you want a very, very flat sheet. So our best answer here is F. It can be split into thin, flat layers because slate is a foliated metamorphic rock or layered. Which of these provides the best evidence of the environment in which an igneous rock was formed? Alright, so igneous rocks are either formed under the ground from magma, and remember that's an intrusive igneous rock. They'll have crystal development such as gabbro and granite. Other igneous rocks are formed extrusive or outside of the Earth's crust. They're formed very quickly as lava reaches the surface. Examples of extrusive igneous rocks would be basalt, volcanic ash, pumice. So which of these would provide the best evidence of the environment in which an igneous rock was formed? Its thickness? No. Its color? No. Its size? No. But its texture. And here they mean texture is the crystal development. Which of these can determine the size of grains in igneous rocks? The amount of rare minerals, the distance from a plate boundary, the size of the volcano, or the cooling rate of molten rock? When they talk about grain size in an igneous rock, what they're really talking about here is the crystals. And remember, crystal development is determined on how fast the rock cools. Rocks that cool very, very slowly underground are called intrusive igneous rocks, such as gabbro and granite, and they have lots of grains and crystals. Rocks that form outside the Earth's extrusive igneous rocks, such as pumice and basalt, have very minimal amount of grains or crystal development. So our answer here is J. The cooling rate of molten rock will determine the size of the grains or crystals in igneous rocks. Students want to identify a rock in a nearby field. Which of the following properties would be most useful in identifying the unknown rock? So if you have a rock and you don't know what it is and you want to identify it, the color could be helpful. It's probably not the best answer. The smell, definitely not. The smell of a rock has nothing to do with which rock it is. The mineral content, if you were able to know exactly what minerals make up the rock and what proportions, you would pretty much know what rock it is. The specific weight or density could be helpful, but it wouldn't be the best answer. So the best answer is H. The mineral content is what can help you identify a rock. Which of the following minerals, when in the form of sand, can be used to manufacture glass? Well, this is just a memory question. What's used to make glass? Is it gypsum? Is it diamonds? Be very expensive glass. Calcite or quartz? Well, the process of manufacturing glass is melting down quartz and then cooling it very, very quickly. So our answer here is D, quartz. Extrusive rocks have small grains because they cool quickly, harden underground, contain rare minerals, have a rough mixture. Remember, extrusive rocks are the cooling of lava, so that's outside of the Earth's crust, and that does mean they will cool very quickly, F. And because they cool quickly, they have very small grain size, and remember, that also means the same thing as no crystal development, so small crystals. So our answer is F, they cool quickly. The presence of many metamorphic rocks in Virginia is an indication that the area has been subjected to, just got to think to yourself and remember what builds a metamorphic rock. And our answers here are always heat and or pressure. So the best answer is A, intense heat and pressure. That's what makes a metamorphic rock. Lightweight and strong, the metal that has been recycled with the greatest success is steel, tin, aluminum, or titanium. What do we recycle the most? And the answer is cans, these aluminum cans. Heat and pressure can transform an igneous rock into a metamorphic rock. But what processes can transform igneous rock into sedimentary rocks? So you remember, sedimentary rocks are made from weathering, erosion, deposition, lithification. So this whole process of breaking down an igneous rock into little chunks and using minerals and the Earth's materials to glue it back together into a new rock. So our best answer is not heat and pressure. That's how we make a metamorphic rock down here. Rifting and subduction? No, that's not how you make a sedimentary rock. Erosion and sedimentation? Yes, that is our best answer. H, erosion and sedimentation. Okay, this was a drag and drop question. We needed to place one of these 5 types of rocks, intrusive igneous, extrusive igneous, chemical sedimentary, organic sedimentary, and metamorphic in these 4 columns. So the first thing you need to realize is that one of these will not be used. Alright, so let's look at what we have here. We have the evaporation of the ocean. Hopefully that's making you think sedimentary rock. We have the compression of the crust of the earth. Now that's going to be a lot of pressure. So hopefully that's making you think metamorphic rock. We have the sinking of plankton. Remember, plankton's a little animal, so we have basically the remains of a little tiny animal making a rock at the bottom of the ocean. And we have the formation of granite underground, so magma cooling under the ground. So let's look at these kind of quickly here. So compression of the crust, metamorphic. Take metamorphic right there, heat and pressure. All right, formation of granite underground. This is the cooling of magma, so it's going to be an igneous rock. So is it intrusive or extrusive? The answer is an intrusive rock. So we're going to take that right down here. And then the sinking of plankton. This is a living material. So our answer here is going to be an organic, for living material, organic sedimentary rock. So we'll take that right there. And then our last thing we have left here is a chemical sedimentary rock, and that's an ocean evaporate. So that goes right here. So one more time, double check, see if you got the right answers. We have in our first box a chemical sedimentary rock. Then we have a heat and pressure metamorphic rock. Then we have an organic sedimentary rock, remains of living things. And then we've got an intrusive igneous rock at the bottom. Okay, which is a characteristic of all non-foliated metamorphic rocks? And our key word here is non-foliated. Remember, metamorphic rocks come in 2 major types. We've got layered rocks, like you can see the schist, see the alternating layers of dark and light bands. We've got slate, which is a very foliated rock that can be split into thin sheets and used for like roofing shingles or a pool table. And then we've got other metamorphic rocks like this one, like phyllite and marble, that have no banding. These are called non-foliated rocks because they don't have layers or banding. So our best answer here is, which is a characteristic of non-foliated metamorphic rocks? Presence of fossils? No. Cleavage planes? No. The lack of banding? Yes. Our best answer here is C, lack of banding. If you remember, the mineral mica kind of flaked apart really easily. It has very, very weak bonds right along its flat parallel layers, and they can be split really easily. Alright, so the cleavage is the way a mineral breaks or a rock breaks. The cleavage properties of mica result from the alternating layers of silica and aluminum? No. The weak bonds between flat layers? Yes. Strong covalent bonds within dense carbon? No. Metallic bonds between all elements present? No. It's B, the weak bonds between the flat layers. Just a memory question. Which mineral is most likely an ingredient used in baby powder? And if you remember, the softest mineral there was, it was talc. You can has a hardness of 1, and you can just kind of rub it together and get this powder right here. So our best answer is not graphite. We use that for writing. Not pyrite. Remember, that was fool's gold. Not corundum. That's a very, very hard mineral. Would not be very good powder. The best answer is talc. D. Which of the following properties refers to the colored powder resulting from rubbing a mineral against a harder surface? Our best answer here is, if you remember, we take a mineral and we rub it across this plate and we take a look at what the streak is left, and it kind of gives you a true indication of the color of the mineral. So this is called the J, the streak test. Remember, cleavage is how a mineral breaks. Its hardness was on that Mohs scale of hardness. Its luster is kind of how metallic or how shiny it looks. So our best answer here is J, the streak. Metamorphic rocks, whose minerals are arranged in layers or bands, are called, and remember, metamorphic rocks, the key words here are foliated or unfoliated. Remember, clastic and non-clastic, that's the types of sedimentary rocks. So our choices here are foliated or unfoliated, and rocks that have their layers that are arranged in very distinct bands like schist or slate, those are called defoliated rocks. So our best answer is D.